I am pleased to introduce our research paper entitled Self-distillation for Surgical Action Recognition. In chemistry, distillation denotes the process of separating components within a liquid mixture. So, what is self-distillation in the context of deep learning, and how can we use it to solve some of the methodological challenges we face in surgical action recognition? This is what the talk is all about. We present our submission to the Codec Triplet Challenge. This challenge introduced a dataset comprising 100 classes, each composed of triplets denoting instrument, verb, and target. Notably, these 100 classes exhibit significant imbalances mirroring the real-life scenario of surgical procedures, where certain instruments, such as graspers, are more frequently employed than others. Another challenge is label ambiguity, represented in triplets sharing one or two similar components, such as the grasper and the gallbladder in this example. On the top of that, a technical challenge is to account for the temporal information. So, how did we tackle these challenges in our submission? An obvious idea is using multitask learning to leverage the fact that we have labels for the individual instruments, verbs, and targets. Similarly obvious is the use of recurrent neural networks given the sequential nature of the data. Additionally, data augmentation and model ensembling techniques are common successful strategies, as also shown in our recent CVPR paper, Why is the Winner the Best? In this short pitch, I will focus on the component which makes our method unique, which is the self-distillation approach. Our hypothesis was that self-distillation can address the challenges attributed to class imbalance and label ambiguity. So, what is self-distillation? Self-distillation is derived from knowledge distillation that primarily seeks to compress a model by transferring knowledge from a large teacher model to a more compact student model. In contrast, self-distillation involves the internal transfer of knowledge within the model itself. The central objective of self-distillation is to enhance the model performance. Our primary backbone architecture is the Swin Transformer, and our approach is structured as a two-stage process, with the first stage involving the training of the teacher model. Subsequently, the teacher model is employed to predict soft labels for the training dataset. These soft labels then serve as an input for the student model that minimizes the loss between its own predictions and those generated by the teacher model. This iterative process facilitates the student in learning from the teacher's errors. One illustrative instance of errors made by the teacher model includes assigning a higher probability to classes that exhibit greater semantic similarity with the reference. This tendency arises when these classes share a common component such as the bipolar instrument in this example. Another example of errors is if an instrument is clearly visible but not mentioned in the annotation, the teacher's model's ability to recognize and predict missing details is an advantage. Our five-fold cross-validation analysis consistently demonstrated the benefit of each of our components: self-distillation, multitask learning, and ensembling. The biggest performance boost was achieved through self-distillation methodology. As you all know, internal validation can be subject to overestimation of performance. So, how did we perform in the challenge? We finished in the first position as our self-distillation based method outperformed other methods that primarily relied on multitask learning or sequential models. To recap, our presented methodology entails a multi-stage process. It initiates with the training of a teacher model using hard labels. Subsequently, this teacher model is employed to generate soft labels for the training dataset. Finally, these soft labels serve as the basis for training the student model. In conclusion, we were, to our knowledge, the first to apply the concept of self-distillation in the context of surgical data science. Hopefully, it will also be useful for you.